So here's the implementation of the compiler. It's going to type case on an exp and produce a corresponding xd. Num-e's go to num-d, plus e goes to plus d, and so on. For IDE, like a name x, we need to turn that into some number. But to know the right number, we need to know more about the context where this variable appears. For example, going back, this x here gets translated to 0, but that's because it was the enclosing lambda that gave us an x. So we need something at compile time that's similar to the environment, and we'll call it env, but it's an envc. This is a compile time environment. And the way that IDE uses the name n is going to be to call a locate helper function with the name n and the environment. And that should give it a number, like 0, 1, 2, and so on, that will wrap with @d. If the name is not found in the compile time environment, then locate will complain with a free variable. Names get added to the compile time environment by a lambda form. So as we're compiling the body of a lambda form, we don't use just the environment that we had, but we extend that environment with the name n. And here we're using bind e instead of regular bind. That is saying that at compile time, we are just recording the name. We don't have a value yet. We're not interpreting. We can't record the name with a value, but we can record the name in the environment, and then locate will be able to use the shape of that environment to predict where the name will be at runtime. So after we compile the body, we just wrap it back up in a lambda. The helper function locate is going to use compile time environments, which is just a list of binding C. And a binding C is like a binding, but it has only a name inside of it, not a name and value. And locate's job, if it gets a name in an empty environment, then that's a free variable. Otherwise, if the name is the first thing in the list, then we know at runtime it'll be the first thing in the environment as well. Otherwise, we look in the rest of the environment and add 1 to it. Finally, we will need to interpret our compiled expressions. And interp for an exp_d looks very much like the interp for exp. The only differences are here at @d and lambd. Actually, lambd is not all that different because we just remember the expression in the environment. We don't have to remember the name anymore. When we apply a function, then here is where we used to call extend_env with an argument name and a value. Now we just have a value. So, and we're just going to use cons directly to reflect that these are always going to be implemented with lists at runtime. And @d, that's implemented with just listref. We have predicted exactly where in the list, in the environment list, the value will appear. And so we can just use the primitive listref as a kind of built-in direct access to that position. Now if we take this interpreter and we run an example, and we run it enough times, then we'll be able to tell that we are in fact saving work at runtime by doing this compilation. Direct access via the numbers is going to be faster than doing a search at runtime. And we can see this even in Dr. Racket. So here I've got our regular kind of interpreter on lambda's form. We've got parse, we've got interp, we've got lookup and some test cases. And at the end of the test cases, I've included this timing test where we're going to take that expression that was on the slides and interpret it 10,000 times and see how long that takes. That was 135 milliseconds. And if we go over to our compile version, so we've got exp and exp_d, and then we have parse, which produces exps, and then compiles, that takes an exp to an xd, and an interp that works on exp_d, so this is where we're using listref instead of a locate based on looking up names. We've got test cases here, and you see the test cases are all test interp of compile of parse. And we now have to compile programs before we interpret them. The compile step changes those symbolic names to position references. And we've got the same example here, the same 10,000 times. Let's see how long that one takes to run. So 102 milliseconds instead of 130 milliseconds. You shouldn't take this actual number too seriously because we're running inside of Dr. Racket, which is doing a bunch of debugging instrumentation, and it's competing with the software that's recording my screen. But it does reflect a real speed up. If you were to run things in a more reliable environment, it reflects doing less work with a listref than having to walk and search for names with comparisons.